Hi, I am Akif Çağlar. In this video, I will present you my term project, which is focusing on a paper with bringing new implementation of KNN algorithm, another approximate neighbor, closest neighbor search algorithm, alternative to KNN. So let's move on to my outline. I will start with algorithm explanation. Then I will move on to simulations on algorithm, in which I make experiments on hyperparameters of the algorithm I am focusing on this project, and then I will make comparisons with the classical method KNN with the new method examined in this project, and then I will move on to conclusion. So let's move on to algorithm explanation part. This algorithm is called hierarchical navigable small word graphs. This algorithm is an alternative algorithm to KNN search algorithm. It is based on a proximity graph. In proximity graphs, links are based on the distance between the vectors. And this algorithm is developed by getting inspired from two other methods. These are called probability skip list and navigable small word. I will briefly introduce these methods to explain the algorithm of this project to you better. So let's move on to probability skip list. In this probability skip list, different layers of with different scales of dynamically linked lists are hierarchically set on top of each other, and you start to search from the top layer, in this case layer 3. In layer 3, dataset is expressed in a sparse sense, so you are making search faster, you are moving faster, but missing some data points between your steps. So when you exceed the value of your query, you know that you have to go one layer down to a denser layer to make a more dense search, more accurate search. The step by step you are moving down to bottom layer, in which all the data points from your dataset is present, and you are finding the closest value to your query in the bottom layer. These hierarchical layers are also used in the algorithm I am trying to explain. So this is where the idea comes from. The other method is navigable small word. This method is also proximity graph based. Its main idea is using links in different lengths. The main purpose is starting to search with long links, so you are starting to search in a sparse way and getting the distance covered faster. And as you get closer to a local minima, links are getting shorter, so you are making more accurate, more dense search there. This algorithm uses greedy routing, which traverses to node which has smallest distance to your query value. Let's move on. And this is the figure of our algorithm. This is the general structure of it. It has layers like in the probability skip list, and it has similar approach to that probability skip list. You are starting from the top layer, which has a sparse representation of your dataset, and once you find the local minima there, you move on to layer below, where denser representation of your dataset is present, and again when you find your local minima, you move down to another layer. In this case it is the bottom layer, layer 0, and it has all the data points from your dataset, and you try to find the closest neighbor to your query value. It includes the hierarchical layers from the probability skip list, and sparse to dense navigation, because you have to use the sparse layer first, and different link lengths, because at top layers links are longer, so it has that quality from the navigable small word algorithm. So these are the parameters of this novel algorithm HNSW. EF is the size of closest neighbors list. So it is about the candidate points you are tracking during search. A larger EF gives you better recall and larger query time, because you are doing more comparisons within the dataset. N is the number of links created per node. So higher N gives you better navigating possibilities in the dataset, in the graphs of the dataset. So it is a higher M is better for datasets with high dimensionality. And EF construction is the EF value used during construction. So higher EF construction makes you construct a better graph, a graph with better connections. So it is also important for complex datasets. So let's move on to experiments part. These are the datasets I used. They are in 3 different scales, easy to hard. They are listed here. They are iris, handwritten digits, and MNIST datasets. So let's move on to my experiments. In this experiment, Fisher's iris dataset is used and EF parameter is examined. Here I increase the EF parameter and I observe that recall increase as I increase the EF parameter, because when you make more comparisons during your search, you are covering a larger part of the dataset graph space, so you are more likely to find correct local minimas than false ones. So you are more likely to find the closest neighbor to your query value. But it also increases the query time, because you are making more comparisons during your search. Let's move on. Here we are changing M value. As you can see, M value, the benefits of M value saturates after some points, because you have enough connections to navigate your graphs sufficiently. So in this case, in iris dataset, the required M value is like 5, but it will increase as we move on to more complex datasets. Here, M value, would expect to see query time increasing with M value, but it first decreases. I think it is because when you have more connections, you are faster to find your local minima, so you are able to finish your algorithm, finish your query faster. But after some point, after the benefit of M value has ended, the increasing M value increases your query time. Here EF construction is tested in iris dataset. As I said, the higher EF construction gives you a better graph structure, so your recall increases because of the better graph, and it does not has a direct effect on query time, EF construction in this case. And here we move on to handwritten digits datasets. The same observations are valid here about EF, but what can we notice is that the used EF values is much higher here to have a performance saturation. It is around 40. It was around 10 for the iris dataset. It is increased due to increasing the complexity of the dataset. So M value, again, it was 5 in the iris dataset, but here we are using 15 to have a saturating result, saturating recall at a high value. M value also increases the query time, like in the iris dataset. And EF construction, it has the same observations again, but here there is a jump of performance here. At value of 30, EF construction is being equal to EF value used during the search. The search EF value, it is 30 here in this experiment. So I think it might be the reason that EF construction catching up with the EF search value is giving this significant performance boost. Let's move on to MNIST dataset. We have the same observations about EF parameter, and about M. We see here we need about 35 M value for saturating recall performance, because it is the most complex dataset used in the experiments. And about EF construction, we have to use around like 100 here to get the best possible graph. It is because there is so many elements in this graph. You have to use a higher EF construction value. And this is the with the classic K-NAN algorithm. Here in Iris dataset, their query time is almost the same, but as we move on to handwritten the digits dataset, the query time difference is like 8 times, and at minutes dataset there is 600 times of query time difference. So in complex datasets you have to use HNSW or a similar approximate search algorithm instead of KNN, because KNN cannot scale well with the datasets, and the search time becomes unfeasible after some point. So in conclusion, we have talked about the parameters of HNSW algorithm and its background theory, and we have made simulations about its hyperparameters, and also we have done comparison with the K-NAN algorithm, and we saw that it is feasible to use in very simple datasets, or in cases where query time is not an issue. But in complex datasets you have to use HNSW algorithm. These are my references, and thank you for your attention.